Finally, we are ready for the conclusions. Let's say we have some sort of airfoil, and we would like to build an airplane around this airfoil. So we're going to build a wing using this airfoil and so on. So the question is how this plane is going to perform. What is the longest distance I can fly? What is the longest time I can stay in the air? What is the optimal condition of flight? What is the optimal speed to fly this plane with this given airfoil, and so on. So in this video we're going to answer all those questions. We're going to plot the efficiency curves for the optimal duration, for the longest flight duration, for the longest range, and so on. But first let's go back to the high school and recall those equations from the previous video. So the lift force is given by this equation, drag force by this equation, lift and drag coefficients follows from those equations. Where Q is dynamical pressure. Then we can divide one equation by the second one. So lift force divide drag force divided by the lift force. We're going to receive drag coefficient divided by the lift coefficient, and hence we can introduce beta constant proportional to lift coefficient divided by the drag coefficient. This number is going to be useful in the next section, so we remember this. Next, what we can do, we can derive the drag force, which is follows from this equation if you plug those things inside. So the drag force is proportional to the mg, mass of the airplane multiplied by the acceleration, free fall acceleration, and divided by the beta constant. Useful equation. The lift coefficient, again this equation from here, can be written as mg divided by qs, where q is dynamical pressure. And now one more equation from the high school. The energy is equivalent to force multiplied by the distance, and the distance is speed multiplied by time. So from here we can extract the distance, which is equivalent to energy divided by the force, drag force in our case. And then if we plug the drag force, we're going to have this equation. And from here it follows that the flying distance is proportional to the beta divided by the mass. So if you would like to have maximum flight distance, you have to maximize these things, beta divided by mass. The same as for time. You can extract time from here. So you divide energy by the drag force multiplied by speed, and then you plug the drag force, and eventually you get the time proportional to the beta divided by the mass multiplied by the speed. If you would like to have the time of flight maximum, you have to maximize this thing. Okay. So the simple conclusion that what we would like to have is to have maximum ratio between lift coefficient and drag coefficient. So beta has to be maximized. And the second conclusion is that mass is not your friend. Keep it small. Well, in reality, beta is not a constant. In reality, it depends on the speed, and it also has the lift and C drag coefficients have strange relations sometimes, and the beta is constant only in narrow range. So in general case, it's going to be different for every point and for every speed. The problem itself is not complex, but let's see it more clearly by looking at the concrete example. So let's say we have an airplane with mass m and wind loading. So those are given. Wind loading is the ratio between mass and wing area. And the question is find the optimal speed and find the optimal speed for maximum distance and for the maximum time in the air. So and let's say we have an NACA airfoil 0009. So NACA airfoils, we have to remember that those are built for high Reynolds. Those were designed for high Reynolds number, and for the low Reynolds number are not good, actually pretty terrible. I'm interested in this example for the low Reynolds number, but I will use NACA just to see how bad is bad. So we have NACA airfoil, and then we have the aspect ratio is given, so the wing has a ratio between the length to the chord equivalent to 10. Then we have mass of airplane, we call it a drone, 1 kilogram, and area of the wings 0.1 meter squared. Thus the wing loading is 10. Then we have the parameters of the atmosphere. So let's say we fly not so high, actually close to the ground, let's say temperature 15 degrees. And then the density of air is approximately 1.2 kilograms per meter per cubic meter. Okay. So the first thing is, so the problem is pretty simple. So the mass is given and the area of the wing is given, or the wing loading, doesn't matter. So we have the airfoil, so the airfoil is given, and we have the wing defined by the aspect ratio. So, and then some parameters of the atmosphere. So it's pretty simple. So the first step is actually look at the speeds that we are going to operate. So let's say we would like to operate at some range of speeds, let's say from minimum speed to maximum. So we divide this interval into the number of those speeds, and we need to do it because for each speed you're going to have different Reynolds number. So the Reynolds number is proportional to the speed and to the chord length, and given by this equation. So you can derive it, but I have done it already. So this is the Reynolds number, and we have to, for each speed, have different Reynolds number. So next thing is to plot this graph. So we have lift coefficient on the y-axis and drag coefficient on the x-axis. So for the foil we have the red curve. So this is two-dimensional foil, and the results can be obtained either from the wind tunnel or from the X-foil software. So we have this curve. So this curve depends on the Reynolds number, thus depends on the speed, because we have this dependency. So it's going to be different for each Reynolds number and for each speed. So we're going to have, like for each speed, you're going to have this red curve. So this is one thing to keep in mind. And the second thing is that in this case, we don't care about the airfoil anymore. So airfoils are looking good, but we do care about the airplane performance. So we have to include the wing in the picture. So how to include the wing? So I have done it using a very simple method. So the first simple approach is to use XFL R5 software, and the second approach is to use analytical equation for the wing. So actually, what we can do, we can use induced drag equation. So this equation, if we plug those numbers, R is the aspect ratio of the wing and E is the quality factor, has to be 1. So if we plug those numbers and we add this induced drag to the total drag obtained from the X foil, we're going to receive the following results, which actually are the same as the software we use. So this software, XFL R5 software, gives us the same result as this simple equation plus X foil simulation. So the dashed line is analytical result, and the solid line is a result from the software. So at least for the simple wings, for the square wing, we're going to have the same results for this simple equation plus, so this simple equation, analytical equation, plus the results from the X-foil software, and we're going to have the same results as result obtained from the XFL R5 software using VLM2 method or similar method that are available in this software. Okay, so if you do this, we're going to have the blue curve. So the blue curve is the curve for the wing. So kind of the red is the 2D foil simulation, and the blue curve is the simulation for the wing. So as you can see, if for given aspect ratio, if you increase the aspect ratio, this curve is going to kind of approximate the two-dimensional X-foil results, because you can think about this as if you extend the wing, make it longer and longer, it kind of becomes 2D, not 3D wing. So anyways, so wing is going to be computed in this way, and we are ready for the next step. And the next step is to find the lift coefficient. And the lift coefficient is, as we have seen previously, is given by this equation. Q is dynamical pressure. In this case, it's going to depend on the speed of the plane. And if you plug the equations, we're going to have this result. If you plug the numbers and you calculate, you're going to have a very simple equation. So the wing loading divided by the speed of the airplane squared multiplied by 16. Actually, 16.0 something. So this is the equation that we need. And now I would like to make some nice observation. So like if you look at this equation, you have the density of the air inside. And now imagine that what if you are going to reduce the density of atmosphere? So what if you're going to go higher? Or what if you would like to fly on some other planet, let's say on Mars? So if you, let's say, if you decrease the density, let's say in 100 times, make it 100 times more dense, then you would have to increase the speed 10 times, because you have square. So if you like to high at altitude where you have not 1 kilogram of molecules per cubic meter, but let's say 100 grams, 10 grams of molecules, then you would have to fly 10 times faster. So this is a good and fun observation. And another observation is, let's say if you like to go higher and higher and fly higher and higher, then you would eventually reach the speed, because you have to increase the speed. You're going to have reach the speed, the orbital speed. So eventually you're not going to be a plane anymore, but you're going to be a satellite of the planet. So on this speed, you're going to have the certain, so you know the speed of the orbital objects of satellites. I think it's 7 kilometers per second, something like that. So from here you can know the density of atmosphere. And knowing the density of atmosphere, you can find the height at which you have this density. And this height is approximately 100 kilometers, and basically the area of the Earth's atmosphere. So that's the way how the space is defined. But yeah. Okay, so the second step, you have to find the lift coefficient that is needed to lift the plane for the given wind loading and for the given speed. Next, if you know the lift coefficient, you can from those curves obtained by X-foil, you can get the drag force, drag coefficient. So from lift coefficient you can get the drag coefficient, and then you can get the beta number by dividing lift coefficient by the drag coefficient. And what you can do now, you can plot finally beta, because beta is the efficiency, as you have seen previously. So beta is here, so you know what you have to maximize. So you have to maximize beta or beta over speed. So you can plot finally those things and see what you have as a result. And if you want, you can compute the power of your motor by multiplying, by dividing mg of the airplane by the beta. Okay, so let's go to the results. And I have plotted those curves already. So CL, lift coefficient over y-axis, and drag coefficient over x-axis. As we have seen previously, those are polar graphs. So each curve corresponds to a specific speed. So we have different speeds here. in the range of my interest. And for each speed I have different Reynolds number, and for this for the given Reynolds number I have the specific curve. So I have my different curves with different Reynolds number. So to plot those curves, what you can do, you can write a script to control Xfoil, so that you don't have to do it manually, or you can use this software. Boom. So XFL R5 software is very good, very convenient. It has uses the same source code, but instead of running Fortran, it uses C language, and for whatever reason it's run, as I think it runs faster, and it's also became more stable. I don't know why, but it's more stable and faster. So I really kind of fan of this software. So to run the analysis, I have showed this in my previous video. But analysis, then press this, then choose for the given airfoil. You specify the range. So you specify the range. In this case, let's say you have from 60,000 to millions, and then you can choose like any increment you wish. It's actually pretty fast, so you don't have to like leave it for 1 day or so. And then you use the range for the angles of attack, and then press analyze, and it's going to be going to see the results. So the one remark is that about the range, the alphas. From that equation, for the lift coefficient, we know that this lift coefficient is inversely proportional to the square of the speed of the airplane, so speed of the airplane. So if you fly fast, let's say 70 meters per second, so you don't have to have high lift coefficient. You can have it small, and lift coefficient is proportional to the alpha, so you can use small alphas for the high speed, and maybe use few graphs with high alphas range. Maybe like for the small speed you can have a few results with high alpha, and the rest are good enough for the small alpha. So in those graphs you can see that I have plotted only a few curves with big range, so from 0 to maybe 8 degrees or 15 degrees. But the rest at the high Reynolds number, I have small range to only 4 degrees or one less. Okay, so this is the curve. Beautiful looking curves for our analysis, but unfortunately we're not in the business of 2D foil analysis. We are serious here, and we would like to have results for the 3D analysis of the wing. So we use this beautiful equation, and once again I have proven that gives the same result, this simple approach as this software. So I don't have to run the software, don't have to go here, at least for the simple wings, and I have to run simulation in this software. So we use this simple equation, and we know the C-lift coefficient. We know the C-lift and C-drag coefficient were obtained by Xfoil or some other software. So you just plug lift coefficient here, and you get the different drag, a bit different drag. And on x-axis you're going to have a bit different scale as a result. And if you look at those two graphs, the series of those curves, you will note that for the wing case, so this is the wing, we have kind of more tilt. That also makes sense, because more tilt meaning that for the same lift coefficient as here, you're going to have more drag. So you have more drag because you have a wing, not a 2D foil. So this is done. So after that, what we do, we look at once again at this equation, and the lift equation. So lift equation is proportional to the square, is inversely proportional to the square of the speed. So for instance, what we can do, so now we in the wing section, so what we can do, we look at the speed, say 10 meters per second. So what we do next, we compute the lift coefficient. We compute the lift coefficient by this equation, so we know the lift that we need. Then what we do, we go here and we look at the lift coefficient that we need. Okay, somewhere here, let's say 0.7. Then we project line to the curve, corresponding curve. For this case, it's the speed 10 meters per second. And after that, we drop line down and we can find the drag coefficient. So I have drag coefficient. So I have those dots, again, computed automatically with Python. So I found all the C lift coefficient that I need for all the given speeds, and then I found the corresponding drag coefficients by dropping the curve down. And I have those points, boom, boom, boom. So those are the points where the lift and drag pairs can be found. And once again, you can note that for the small speed, we need big angles of attack, so the point is somewhere here. But for the high speed, it's close to the, well, it's a red range, so we have high speeds here. We have the speed approximately above the 40 meters per second. So all the points are down there, so you don't really need the lift coefficient high, and don't really need to have a high alpha, so maybe just a few degrees sufficient, maybe even less than 1 degree. Okay, and so to do all of this, I have been using my Python script. The script is pretty simple. So what you do here, you just you have a loop, and this loop, what it does, it reads the files that we have saved from the software. Yeah, one remark. So in this software, we save all the files. We have computed those beautiful curves, and then you go here and choose polars, and then export all, and then select here and where you want to have them. So as the result, you're going to have those things. So you're going to have all those files in the folder. Each file has structure, given structure. So you can get all those files in the folder, and then you run the Python script. So the Python script, what it does, it has the loop, and this loop, it goes from file to file, and it puts the data from the file to the kind of vector format that we can use. So we have vectors alpha, angles of attack, lift coefficient vector, drag coefficient vector, and so on. And then what I do, I just plot the result in the loop, and I have those beautiful curves as a consequence. Oh, and I also display the data. For example, this is the lift needed. So at some speeds, for example, if you would like to fly at speed 4 meters per second, you would have to have lift coefficient equivalent to 5.5, and there is no airfoils which can give you that high lift. So you cannot fly at some speeds, and then you probably can fly at this speed, 11 meters per second. So, and then you have those points. So automatically I got the lift coefficient needed, and then I found the corresponding drag coefficient, and thus I can compute the beta constant. So the beta constants can be plotted as well. So here's the beta, so the ratio between the lift coefficient and drag coefficient. So for each point I have the ratio between the lift coefficient and drag coefficient, and I can plot this ratio over the v-axis. So I have certain ratio for the given speed, and then I have this point for the speed, and then I can plot the ratio on the y-axis. So I have many points, and then I have the results already. So my Python, so I have the code for the plotting of these efficiency curves. So what I have here, I have the first curve is beta itself. So the beta is the red curve. It has this interesting shape, and we would like to have this beta maximized. So basically we would have to pick the point which is maximum, again done automatically, and the speed which is corresponding to this maximum position of this graph is 16 meters per second. So, and the second curve is blue. The blue curve is beta divided by speed. We know why, because we would like to maximize beta, and beta divided by the speed to get the maximum flight duration. So blue is the curve for the maximum flight duration, and again we find the peak of this curve, and the speed is a bit different, so a bit smaller, 14.6 meters per second. So if you fly at this speed, you're going to fly maximum time. If you are going to fly a bit faster, 16.1 meters per second, you're going to fly the longest distance. Okay, so those curves are good, but we also have from the database we have extracted angle of attack vector, so we can plot those curves over the not speed but angle of attack. No, so we can have the speed axis, and instead of beta we're going to have alpha, angle of attack. So again, what we do is just basically curve for the same. We basically choose the speed, and at each speed we're going to put the alpha, because so the beta parameter is slip coefficient divided by the drag. Slip coefficient is related to the angle of attack, so we can plot the angle of attack instead of beta. So here's angle of attack is plotted over the y-axis, and here is the speed, and here's the curve. So the angle of attack is dropping as the speed increasing, which totally makes sense, because if you have small speed you would have to have high angle of attack, but eventually the optimal point are occurring at given speed, 16 and 14 meters per second. So we can plot those points here, and then we have the corresponding alphas again computed automatically, and the alpha is for the maximum distance is 3.2 degrees, and alpha for the maximum flying time is a bit higher, 4.2 degrees. Okay, so this is the Python code, and the results I have shown already in those graphs. So those are the efficiency curves, and this is the alpha that we have to fly the maximum distance and the maximum duration and so on. Okay, so this is simple. Okay, and now let's play with the aspect ratio of the wing. And we're going to use this simple equation. As I have shown previously, it's going to give us the similar results to what the real simulation is give us. So you can either run this software and get the results, but it's going to happen a bit slower, or you use this simple equation and you will obtain the same basic curves. At least for the simple wings, you're going to have the very similar curves. So there is not much of a difference between the XFLR5 simulation and the simple equation. So we're going to use this simple equation to play with the aspect ratio of the wing, and we also have to make a few notes that if you let's say increase the aspect ratio of the wing, you would have to either increase the space, the area of the wing, or you would have to reduce the chord length. So if you reduce the chord length, you would have to change the Reynolds number, basically make it smaller. Or if you increase the area of the wing, you're going to have a bit different results for the lift coefficient. But for the first approximation, just to see what's going to happen, it's sufficient not just to touch anything and just use this equation. So plug it instead of drag for the X-foil, and then you're going to have those curves. So those curves you have seen already. This is the aspect ratio is 5. So we have the 2D foil, and we have tilted results for the wing, meaning that we have more drag for the same lift. And now let's go to the aspect ratio 20. So we have longer wing In that case, so this again, the same graph for the 2D foil. The same graph is here, nothing changed. But here's the wing, and we know that here's the angle at which those curves are rising a bit higher. So we have less drag than we had in previous case. For the aspect ratio of 5, we have more drag than for the aspect ratio of 20. So again, we got the same points for each speed. We're going to find a point on corresponding curve and then find the corresponding drag, and then having the lift coefficient over drag coefficient, we're going to plot the efficiency of this wing. And here is the result. So again, so B goes to max, and if you look at the numbers, you're going to see that the speed is a bit lower. And here is the alpha, the angle of attack that is needed. And what we can do, we can also plot those graphs on the same kind of on the same side by side, so that we can compare the results. So here is the wing with aspect ratio 5, and here is the wing with aspect ratio 20. And we see now that for the long wing we need a smaller speed to operate in the optimal point. Let's say in this case, for the maximum flight distance, we would have to have 16 meter per second speed. Whereas if you have shorter wing with aspect ratio 5, you need high speed, 18.3 meter per second. So for the longer wing we have smaller optimal speed. As a result, we have higher angle of attack. In this case we have 3.2 degrees, whereas for the aspect ratio 5 wing we have 2.2 degrees. So we have smaller speed, and we also have higher angle of attack as a consequence. But there is also something else. If you look at the efficiency at beta, so it's lift coefficient divided by the drag coefficient, we know that for the long wing we have efficiency approximately 28. So the lift coefficient 28 times higher than the drag coefficient. Whereas for the shorter wing we have a small number, approximately 18. Okay, but what does it mean? So we have beta 28. If you look here, like in this equation, so the drag equation is equivalent to mg divided by beta. So basically, if you divide mg by 28, you're going to have a pretty small number. So you're going to have 3.5% probably. So to keep this plane in the air, you need only keep not the whole mass of this plane, but you need force to keep only 3% of this plane mass. Basically, for instance, if you have a drone and you fly a drone, then you would have to keep the mass of the drone all the time. So you need the engine or engines with thrust equivalent to mg. Whereas for the plane, you have to divide this mg by the beta, which is, in the case for the long wings, almost 30. So you need around 3% of the power if you compare it with the power of the drone. So that's why planes are cool. You cannot do this on drone. So on plane it's very efficient. Or you can think about this in a different way. You can stay in the air 30 times longer than in the case of the drone. Or you can fly distance approximately 30 times longer than in the case for drone. So planes are cool. And also for the long wings, we know that they use gliders. The gliders usually have long wings because, again, it's more efficient. But as a side effect, you would have to fly a bit slower. So long wings mean that you have to fly slower, and to be in the, it does not mean that you cannot fly it fast, but to be in the optimum position, you would like to fly it a bit slower than the plane with the shorter wings. And this is totally makes sense. It totally makes sense, and the conclusion that we have obtained definitely the same as we can see in the reality. Okay, so this is the aspect ratio. Aspect ratio results. You should have longer wings to fly longer distances, so stay in the air for longer time. You also like to have a bit high angle of attack, and the plane is very efficient. So to sustain the plane in the air, you need not the whole. You have to have thrust not equivalent to the whole weight of the plane, but just a small fraction of around 3%. Okay, so what else? What else? We can play with the mass. We can try to compute the results for different mass. Let's say we have mass 1 kilograms, or mass 0.2 kilograms, or mass equivalent to 5 kilograms. So I would say right away that 1 kilogram is a good mass for this plane, because we kind of get our points around the curve, around the efficiency, around the polar curve at different spots. But if you change the mass a bit, you're going to kind of reduce the operational range of the plane to a very narrow segment. So let's say we're going to reduce the mass to 0.2 degrees. So in that case, what you have points only somewhere here, because they need to have high lift. It's efficient to have small lift. So basically you stay in the linear range of those curves. So those curves have approximately the same shape. It's kind of straight curves. So you stay here, and there is not much interesting things happening. And also for the small mass, you would have to, you can fly at small speed, but you would have to go to the low Reynolds number, and low Reynolds number is a big issue, because the solution does not converge and so on. So you kind of don't want to go to the low Reynolds number, probably not to the 4 meters per second. If you fly there, you have computational problems. So, but if you stay in the reasonable range, so then you're going to have in the basically narrow linear range, and as a result, efficiency curves are looking like this. So the slower you fly, the better is your performance. The longest distance you're going to cover, and the longest time you're going to stay in the air. Okay, if you increase the mass, make it too high, say 5 kilograms. So the only way this plane can fly, you have to go very fast. So you have to go fast, so you don't even touch those curves with the small speed. So those curves are completely out of the picture, and you just stay here at high Reynolds number and high speed. And again, you are in the linear range. So there is nothing like you somewhere here, and then you have a different kind of shape of the polar curve. You just here almost in the straight line. And the efficiency curves are also kind of boring, because you just, again, you have to fly as slowly as you can, but not slow, because otherwise you're going to drop from the skies. So what is the right mass? I think interesting design is when you actually use the whole range of the polar. So when you use all the curve, so you use high lift coefficient and small lift coefficient, so you squeeze as much as you can from the foil. If you use kind of too small mass or too high mass, it's kind of boring design. You just use a fraction of it. So I think that this is the way to go. It's kind of, at least you have fun when you design a plane, not staying in narrow range of operation. Okay, and I think that's efficient. At this point, I can say that I'm pretty happy with the results. I can choose any airfoil I wish, and I see the direct connection to the plane performance. I can look at the polar curves, and it's kind of says a lot about the performance of the plane. Or for instance, I can plot the efficiency curves, and I can maximize the duration of the flight or the flight range. I can change the aspect ratio of the wings, and I know exactly how it's going to affect the plane performance, and so on. So before, the plane was in a way a black box to me, but now the light of knowledge is shining bright through this darkness, and I see exactly what's inside.